So our next speaker is Andrew Saxe. He's pretty familiar to Princeton. He did his bachelor's degree in electrical engineering at Princeton, and then he did his PhD in electrical engineering in Stanford, working with Jay McClend and Andrew. Usually I don't know how to spell his last name. Andrew Inc. And Surya Ganguly. And then currently he is a Sloan postdoctoral fellow in theoretical neuroscience, working along with Chaim Sompolinsky. He have done a lot of work on theory of deep learning and its application to phenomena in neuroscience and psychology. Thanks, Andrew, and looking forward for your talk.
Thanks. Well, thank you very much for having me. It's good to be back here. You've heard a lot about this so far today. There's this sense of mystery surrounding deep networks right now, and we know that they work incredibly well in practice. It's just an empirical result. And I think people have the following intuition about why that is, but it's somewhat vague. I think the benefit of depth is that they compactly represent complex functions in some way. But at least the idea for a while has been that naive deep learning is hard in some sense, difficult to actually train networks. And as one example of this, I'm showing a deep network being trained on the handwritten digit recognition task. And you can see over the course of training, the error starts quite high, and it doesn't really do much for a while until eventually it sort of bumps down towards the global minimum. So this is an example where this deep network seems to get stuck at the beginning, and we'd like to understand this full time course, what's going on with this whole dynamical trajectory here. And so what I'm going to talk about today is maybe the seeds of a clarifying theory. And it's concerned with questions like what role does depth itself play in complicating these learning dynamics? So lots of features of a deep learning setup. You can add lots of bells and whistles, but what is the specific contribution of depth? Are there other important features of the training setup that control the training speed, for instance, the initialization scheme? And finally, I'm going to spend most of my time on this generalization question of how networks generalize, their dynamics of generalization to novel inputs. So there's basically going to be three parts to this. I'll talk about training dynamics, scaling laws, and generalization dynamics. I'm always going to be using this tool of deep linear neural networks, but then you'll see that the results align with the nonlinear models. Okay, so I think particularly for the brain sciences, actually, it's important to have a very simple model. You want to throw away all of the details that might be irrelevant so that you can see the essence of some of these phenomena and get unambiguous predictions. So that's the motivation behind using these deep linear networks. So what is it? Well, you saw it in the last talk, but if here's a standard feed-forward deep neural network where you have these tunable weight parameters and these nonlinear functions f, all we're going to do is throw away all of those nonlinearities. And this will be our simple model of depth and its impact on learning. So what is this object? Well, again, the input-output map is always linear. All we're doing is multiplying a bunch of matrices together. And you could always rewrite that as one single matrix. So you could rewrite this deep network as a shallow network. So you might say, what's going on here? Well, there's no additional representational power from depth, but we'll see that there actually is an impact on the learning dynamics. And in fact, that network that I showed you at the beginning, this is a deep linear network. So you can see that it can give some interesting results. And it also shows phenomena that have been observed in nonlinear networks. For instance, if you first pre-train one of these deep linear networks, it then trains much faster on the exact same task than if you started off with these small random initial conditions. So the goal is maybe we can get some insight. I mean, we are ultimately interested in the nonlinear case, but maybe we can get some insight by studying this linear case. Okay, so just to be clear, because sometimes it's hard to see where the complication is coming in these simple models. The input-output map that we're considering is linear. All right, that's what I mean when I say a deep linear network. But we're plugging it in to a nonlinear error function, of course, right? So here I'm going to use the squared error between some target outputs and the network's output. And then the learning problem is minimizing, with respect to these parameters, this composition of that linear input-output map with the nonlinear function, and that now is non-convex once you have a deep network. So essentially, these are different axes here. You have nonlinearity and you have depth, and you can find algorithms at all points. So a linear shallow algorithm would be the standard linear regression you're used to. Nonlinear shallow algorithm might be support vector machines. You're basically just learning the readout weights from a nonlinear expansion. Deep networks are, the whole zoo, and then we're just filling in this spot here. Okay, so what does gradient descent do in these networks? Well, first of all, this is the gradient descent equation. You see it's actually quite complicated even in these linear systems. So in particular, there's coupling. You need to know all of the weight matrices to know how to change one specific weight matrix. And another important fact here is that the only way that the data enters in the linear case is through the input correlations and the input-output correlations. So that's not true in the nonlinear case, but at least now we can phrase this dynamical question of what are the dynamics of learning in terms of this statistical structure that we're feeding in to this network. So what we'd like to do is solve these equations, solve these coupled dynamics to get some insight into how these networks work. And there's lots of work on this. So the critical points have long been known, and there's recent work sort of firming up the details. So it's sort of stated without proof, actually, in this paper that some of these critical point properties held, but it's recently been proven, as you just saw. Shallow dynamics have been known, three-layer dynamics, even some nonlinear networks, but the goal here is to understand dynamics in deeper networks. Okay, so we want solutions that explain how each weight is going to change over the entire course of learning. And the key difficulty is that these gradient descent equations are coupled. And so what we're going to do is a particular change of variables that will happen to decouple them. And it turns out that the right thing to do is the singular value decomposition. So here's the basic setup. The world provides you a data set specified by this input-output correlation matrix, sigma yx. And we're going to decompose that into the product of three matrices using SVD. So we have our left singular vectors here, then a diagonal matrix of singular values, and our right singular vectors. And I'm going to analyze our network in the same light. So basically, the network is producing its own predicted input-output correlation matrix. And I'm going to do a change of variables by putting in this U matrix and this V matrix, and then analyzing the dynamics that are what's these effective singular values are going to do sitting along the diagonal here. So essentially what this change of variables is doing is revealing that there's hidden 1D networks within this fully coupled system. So once you do this SVD change of variables, you need another assumption on the initial conditions, has to be decoupled initial conditions, but then solutions will stay in this form, and you just get these independent chains that don't interact at all, and that's the key simplification. So let's just pull out one of these chains. If you look at what one of these is doing, basically takes your input x, projects it onto a particular singular vector, and then propagates it through a bunch of linear scalar neurons. So this really is just a 1D chain of neurons, and that is the output that you will generate along this particular output vector, output singular vector. So here these B parameters are like the effective weights between the neurons in this one-dimensional chain, and the overall singular value is just you multiply all those. And that gives you the overall effective singular value. And just in general, I think if you're looking for intuition about deep learning dynamics, thinking about this linear chain case there's actually a surprising amount of interesting behavior that arises even in just this 1D chain, so it's worth spending some time with. Okay, so here's an example of how this works, just in movie form. And what you're going to see is that the dynamics pop up, so these effective singular values pop up along the diagonal, and as they do, it refines the network's input-output map. You may also be worried that, am I sort of giving it the answer by baking in these two matrices here? And the answer is no, because we did this change of variables after we computed the gradient descent equations. So it is the real gradient descent dynamics, just viewed through this lens. If you had done the change of variables first, then it would have given a different result. Okay, so if we look at one of these 1D chain modes, now things get very simple. So here's the error surface. It's just the difference between, so basically now we have the associated variance on the input in this mode, and the singular value, which is our target that we want to eventually be equal to. And all we're doing is multiplying a bunch of scalars together to try to get these things to equal each other. Now I'm going to take an additional assumption, which is that we're going to assume you use balanced initial conditions. So we're going to assume that you just initialize your weights with the same variance scale at each layer, and then you're going to have roughly equal effective layer weights. And then things simplify enough that I can actually show you what these modes look like on a plot. Okay, so here's the error surface coming from one of these 1D chains as a function of this individual layer strength beta for some particular parameters that I've shown you. And these different curves are different depths. And as you can see, if it's a depth 1 network, we just get a nice simple bowl. Everything's convex and there's no issue. But things get more complicated for those larger depth networks. So one note is that there's always a global minimum for all of these networks, and there's really no other minima in this simple linear case. Nothing else can happen. But there is another critical point, and the critical point is a saddle point, and it occurs at the origin. And right next to that saddle point, you can see that there's a plateau. And essentially, the intuition here is if your weights really started off at exactly 0, your network doesn't implement any updates, right? None of your weights change, you just stay there forever, so it's a genuine saddle point. And any randomness will break that symmetry, but you might hang out on this plateau for a while before gradient descent will actually expel you from it. So here's an example of the dynamics that result from this. So I'm just going to start different networks at these different locations here, and you'll see that over time, they eventually get to their global minima, but the shallow networks in this instance are training faster. And this bottom plot is showing the effective singular values. You can see them popping up over time, one after another. Okay, now you can simulate this, but in fact, for certain special cases, you can even get exact solutions. So for a shallow case, that's not very surprising, you can get a solution. But for the single hidden layer case, you can also write down the exact dynamics. And for very deep networks, you can also write down exact solutions. And what those equations look like is this. And I think this is really one of those core differences between shallow and deep network learning dynamics. In a shallow network, you basically just get exponential approach. So it's a very simple scheme. Whereas in the deep networks, you get a sigmoidal shaped curve. So you can hang out. What's happening right here is you're near that saddle point, taking a long time to expel from it, and eventually you do so. And in a very deep network, it sort of lengthens this part, and it's a little more explosive in its shape. So again, I just want to highlight some of the, we made strong assumptions in this analysis that we could get these clear answers. And one that I want to highlight right here is that these solutions are valid if you're starting from small weights. So the dynamics can change a lot if you were to start from large weights, but of course, in practice, this is roughly what people do. Okay, and that's for one single chain, one of these one-dimensional chains. But what this decoupling property says is, if you have multiple chains, they don't interact. So we can now describe what's going on in an entire network. We're just going to have multiple chains doing their thing independently. And so, for instance, here's a shallow network with multiple effective singular values coming online. And here's a deep network with its sigmoidal shapes, multiple singular values coming online. Okay, so as far as training dynamics goes, depth complicates learning even in these linear networks. But you can analyze it, and in particular, the solutions I've shown you are appropriate if you're starting with small random weights, and then you get this sort of balanced initial condition, and you also start off with the decoupled initial conditions that we need for these solutions to be valid. And the principal effective depth in this instance is to introduce sort of sigmoidal trajectories, and those come from this saddle point that appears in the deeper networks at the origin. So this, again, even in a nonlinear network, it's often the case that if you initialize your weights all to be exactly 0, you make no progress. That's the saddle point. And you use small weights, random weights to break that symmetry. But it might take a while to expel. And if you're interested in more, you can see this reference. It has more details. Okay, so next we can move on to scaling laws. So if we have these solutions, we can now ask lots of questions about the dynamics. And in particular, one important question is, if I make my network twice as deep, does it run twice as slow? It's a very simple question, but it's important. We'd like to know exactly how depth impacts the training speed in these networks. Looks like the math got garbled there. Okay, so here's the answer that emerges from these linear networks. Essentially, we can compute the time difference for a limit as the network's getting infinitely deep to learn one of these particular modes as compared to a shallow network. And this will be 1 over the initial strength of that weight raised to the depth of the network. So I guess those arrows are supposed to be subscript and superscript. So what this is saying is essentially the following, that deep learning speed is highly sensitive to initial conditions. And I think you can appreciate that from this error surface, right? So if you imagine that you started with small initial weights, you're very close to the saddle point, then as I make this network deeper and deeper and deeper, this plateau is getting longer and longer and longer, and learning speed will slow down, right? In this regime, deep learning will be very slow. But if I were able to start with much larger weights, for instance, a strength of around 1, you can see all of the curves swirl around this point 1. And then learning would be fast in all of these cases. So this is a general feature of deep networks. They care immensely about the knowledge that's already in them. If there's particular structure to the weights, it can radically alter the training dynamics. Okay, so another thing we can look at is this layer-wise unsupervised pre-training strategy. So this is the observation that even in, this is a nonlinear network here, sometimes it's better to pre-train that network layer-wise in an unsupervised fashion using autoencoders, and then subsequently fine-tune it on your task of interest. And the gap in the start of these curves, basically you spent this many epochs doing a pre-training scheme, and then you started training on the supervised task of interest. But you can see it's worth it because it speeds you up so much in the final learning trajectory. So this is an example of one way where a different initialization can change the learning dynamics. And these deep linear networks show this behavior as well, so we'd like to understand it. Okay, so again, it looks like this has gotten garbled, but the essential result here is that small random weights scale exponentially slowly with depth. And that's because the scale of the learning speed is 1 over that initial strength to the d, the depth of the network. Whereas pre-training and fine-tuning scales linearly. This is because you have to do d pre-training steps, but after that it turns out you've initialized yourself at a good initial weight of approximately 1, so 1 to the d is still just 1, and so learning proceeds quickly. And a final prediction is that, in fact, you shouldn't have to do this whole pre-training fine-tuning scheme. If you just start with orthogonal initialization, that would immediately put you at this regime where learning is quick, and you can get depth-independent training times. This is true exactly for linear networks. For nonlinear networks, it can help, and people have used this, but you might need a correction factor to deal with the compressive nonlinearity as well. Okay, so that's the picture emerging from the training dynamics. But of course, ultimately, what we really care about is generalization, performance on unseen examples. So here I'm interested in questions like, how does generalization depend on the initialization? We've seen that was very important in the training error case. How does it depend on how long you train for, the dataset statistics and the model complexity? And again, I'm interested in the dynamics. So the question is, how does gradient descent generalize, which is separate from other ways that you might train these networks? Okay, so just to motivate this kind of generalization behavior, suppose you're just fitting a sinusoid. Okay, so we have a simple little network here. It's got a rectified linear activation functions, and I'm going to feed in an input x, which would just be the value here, and a bias, a constant 1, and it's going to generate its output y. And we're going to use random weights in this first layer and just train these readout weights. And our target function is just going to be, we want it to be y equals sine x. And we give it only 10 examples, right? So these circles are the sample points that this network has. And we're going to train it with batch gradient descent, right? And of course, if the model is very, very simple, so it only has 2 hidden units, then you can see that its predictions don't really match the sinusoid. Whereas if we make it slightly more complicated, then things start matching the sinusoid a little bit better. But you can kind of go too far. So if once you're up to 10 hidden units, you can get these solutions where it does manage to fit every training point, but the solution has gone a bit haywire. And this is, of course, the bias variance trade-off. Basically, the idea is there's 2 ways things can fail. You can have a model that's simply too simple to even fit your data in the first place on the training set. Or you can have a model that's so complex that it has no problem fitting the training data, but then you haven't estimated your parameters with much precision, and things can go wrong. Okay, but this simple story, you've heard from several people today, seems to be a little tricky in deep networks, because often these massive deep networks can perform extremely well in practice. And we've seen many cases where they can have more parameters than training examples. So here's one of these state-of-the-art image recognition networks, and you can see, I mean, it's just immensely, each of these boxes is itself a complicated neural network. So there's tons of parameters in these models. And if you're a little more systematic about it, this is a nice paper just sort of collating some of these recent results, where the size of these circles is proportional to the number of parameters in these models. And this y-axis here is their generalization accuracy. You can see that these VGG models, they have 155 million parameters, but they're still generalizing just fine. And they're trained on an image data set with only about 1 million examples. Okay, so with this in mind, we can go back to our sinusoidal curve fitting example and just try fitting a 500 hidden unit network on this task, right? So again, it's getting 10 input samples, but we can just give it a go. And in fact, it works very well. Now you can see that the predictions align very closely with the target function. So I'd like to understand how this behavior happens. And again, this was training with gradient descent, starting from 0 initial weights. And we'd like to understand how all of these features are contributing to this performance that you see here. And some people have argued that this is quite a puzzle, because big networks should be too complex and overfit. And that's true if you look at sort of the basic VC dimension bounds or the Rademacher complexity bounds. But this puzzle really, I would argue, is not actually new. So SVMs also generalize well, even with infinite VC dimension kernels. And the basic answer, which was given a long time ago, is that they generalize well if they get a large margin, or equivalently in the SVM case, low norm solution. Right? So ultimately, the solution to this puzzle is somehow the norm of these neural network weights are being regularized. And the question is, where is this regularization coming from? So in particular, there are lots of bounds on Rademacher complexity, for instance, that rely on the norm of the neural network's weights. So if the neural network had small norm weights, there would be no puzzle here. This is just one example. Bartlett has a lot of other recent work on this, and there are many others. So if there is a puzzle, it's where is this regularization coming from? And you might think, well, perhaps it's coming from the noise in stochastic gradient descent. That's sort of one idea that's been proposed. But in fact, if you use full batch gradient descent, you still don't see overfitting. It doesn't seem like that is the essence of it. It may help though. You might say, okay, well maybe it's early stopping. Maybe it's the fact that you're not just running training forever. And so you start with small weights and you just can't get too far away. This gets into ideas of algorithmic stability. But we don't see overfitting even if you train for exceedingly long times. And we'll be able to treat analytically what the asymptotic performance is. So, and then I guess I'll add another one, flat minima. Maybe the issue is, you somehow find flatter minima. But again, in the linear models I'll show you, all of the minima are identical. So that's controlled for here, but they still show this behavior. Okay, so how are we going to look at this? Well, I'm going to make the following setup. Again, it's very simple. This is all linear. In fact, it's even shallow in this slide. We'll get to a deeper version. We have a teacher neural network that's going to generate a data set, and I'm going to feed it to a student network. And the idea here is that these parameters W bar are randomly drawn from a Gaussian distribution, and then I'm going to inject some noise into the output. So this noise is like label noise, right? It's basically flipping some of the corrupting some of the information, the labels Y that you're getting about your data set. And then this will be passed to this linear student network, and the student network has to learn from it. So using this, we can draw a data set of P-training examples, and we just have this simple linear model here. And this framework has been intensively studied, so there's work on its asymptotic error. Lots of other work. Jan LeCun had a paper on this a while ago. But we're really interested in the dynamics again. And additionally, I want to focus on a particular regime, which is the high dimensional setting. Okay, so I'm going to look at the regime where the number of samples is on the order of the number of parameters. So they're both going to go off to infinity. So both P and N are going to go off to infinity, but their ratio is going to be a finite constant. I'm going to call that alpha. It's an important constant. So, in the classical regime, you have tons of data, and you sort of fit a line to it, so it makes sense how that could happen. In the high-dimensional regime, you might have as many data points as dimensions, and then it's much less clear how you would be able to learn in this instance. I think that's the regime that these deep networks apparently operate in. Okay, so what do I mean by generalization dynamics? Well, we're interested in these kinds of training curves, right? So here I'm showing in blue the training error that we've seen an analysis of earlier. But now we can add in, because we have this data generating model, you can exactly calculate what the generalization error is as a function of the weights. And this, by the way, is the true generalization error. It's not estimated from a held out set. Because we have the generative model underlying the data set, you can calculate it directly. And that's shown here. So you can see in this instance, the network starts to overfit eventually. Another comment, it might seem odd why I'm using a random teacher. And I think this is maybe more natural if you've come from a physics background. But the idea is I'm looking for general properties of these learning dynamics. I don't want something specific to one particular problem. And so what I'm going to do is just draw problems randomly and average over them all and look for the average performance. And so we're not interested in any specific problem. We're just saying this is a generic setting where some of my inputs are relevant to my output, and I want to understand how learning proceeds. Okay. So in this case, we can again get analytic results. And we're just basically, again, looking at the gradient descent dynamics and then plugging in for our generative model of our data. We know the fixed point. This has to be going to, this is the pseudo-inverse solution. It's just a shallow linear network. There's nothing else it can do. But we're interested in how it gets there. And again, the tool here is a change of variables, where we change the variables based on the eigenvectors of the input covariance matrix. Okay. So what we need to know in order to solve this system of equations is essentially what the eigenvalues of a random covariance matrix looks like. I'm sorry this has all gotten garbled. It's not going to be very... Mind if I switch to my laptop? Is that all right? Sure. Yeah.
You just unplug it, yeah?
Yeah. I think so. All right. All right, let's try that derivation again. So the learning dynamics are given by this, and we're assuming that your initial weights are drawn randomly with some Gaussian distribution with some sigma W 0 variance. And so we know that the fixed points will eventually be the linear regression solution to this problem. But as I said, we're interested in the dynamics. And the way that we're going to do this is, again, a change of variables. So I'm taking my input covariance matrix, and I'm diagonalizing it using the standard eigenvalue decomposition. And now I'm going to change basis to these z variables, which just rotates into that eigenvalue basis. And again, we're doing this after we've derived the original gradient descent updates, so it is valid to do this. And just some manipulation of this, everything decouples, and now we have dynamics on these z variables that are fully decoupled and depend only on the eigenvalues of this random covariance matrix. Okay, and so when you solve that equation, it's just the first order system. The dynamics end up looking like this. So it essentially has two terms. It says we're going to sum across all of the different eigenvalues of this matrix. And in this first term, you see it's exponentially decaying. And this essentially says I need to forget my initialization. So the size of the initial weights shows up in that term, and that will decay away to 0 over time. And the second term is exponential approach. So it's turning on over time. And you wish it weren't there because it's essentially overfitting to noise. And there's two things that are crucial in looking at this. First of all, you can see that the timescale learning is driven by the eigenvalues on each mode. And the second one is that overfitting is worse when this eigenvalue is very small, right? So the eigenvalue appears in the denominator, which means a small eigenvalue would essentially explode your generalization error. A final comment is if you get a truly 0 eigenvalue, it's exactly 0, then there's no dynamics and no learning in that particular direction. So you're stuck with whatever your initialization is. Okay, so now if we're interested in how a particular model might overfit, we need to understand the distribution of these eigenvalues. If we have lots of small eigenvalues, we're going to see a lot of overfitting. If we have only large eigenvalues, we'll see a little overtraining. And these 0 eigenvalues, they don't play any role because they have no dynamics, but they will contribute a constant error. So what is the typical distribution of these eigenvalues? Well, here we can turn to random matrix theory and the celebrated Marchenko-Pasteur distribution. So this specifies what the eigenvalue distribution is for these high-dimensional random matrices. And it has this general form. So this is the density of the different eigenvalues. And you see it's got this sort of bulk shape. And then it also has a delta function spike at exactly 0, depending on the parameters of this learning setting. So there's the bulk, and it lies between these limits, which are dependent on the amount of data you have. Remember, alpha is the amount of data relative to the number of parameters in the model. And then this spike is all of those directions where essentially you have no data if your alpha is less than 1. So we can now, sort of using this Marchenko-Pasteur distribution, instead of doing a sum over eigenvalues, we can just take the continuum limit. Now we're integrating over this Marchenko-Pasteur distribution. And this gives us theoretical predictions which are valid for the high dimensional regime in these networks. And I just want to draw your attention to some features of these solutions. So first, let's look in this leftmost column. This is the alpha equals 1/2 setting. This is saying I have less data than the number of parameters in my model. You might think this is actually quite like what a deep network, the regime a deep network runs in. What I have in this case is this eigenvalue spike, and then a little gap, right? So there's actually no extremely teeny eigenvalues. There's a little gap, and then the bulk. And what this means is I'm going to have test dynamics that look like this. There's some amount of overfitting, but it's not catastrophic because I don't have extremely tiny eigenvalues. They're either 0 or some finite value. Also, for this sort of standard regime where I have a lot of data, you see the spike completely disappears, and also I have a gap, so I have no extremely tiny eigenvalues, and there's not much overfitting. But the worst case for overfitting is actually the intermediate regime where the amount of data matches the number of parameters. Here, the Marchenko-Pasteur distribution snaps up to the origin. You're going to have lots and lots of really small eigenvalues, and in fact, this will diverge off to infinity if you train it for long enough. So here, overfitting is actually a symptom of having a model that's of intermediate complexity. It's exactly matched to the amount of data you have. And here's just a more systematic depiction of this. So this is showing at different training times how this function looks as a function of different amount of data. And you can see that you get this dramatic spike in overtraining if you keep training for very long times, right around alpha equals 1. Okay, so when you have lots of data, it's not surprising that you don't get overtraining, but you might be curious about what's going on here. Here you don't have much data, but there's no overtraining happening. So what's the intuition here? Well, the intuition is that in this regime, some fraction of your eigenvalues are exactly 0. And those eigenvalues have no dynamics, right? So that's the key thing. Well, you're going to just, there's no learning you can do. You have no data in those directions. So they're going to incur a constant error, but at least you're not going to train on them and get a strangely scaled solution. So that's the issue of a frozen subspace. The other element that's protecting you here is that the Eigengap actually increases in the high dimensional regime. So what I mean here is if you plot the minimum non-zero eigenvalue, right, so you ignore the spike, but look at the other minimum non-zero eigenvalue as a function of different alphas, you can see that it actually increases in both directions. Right? So you're getting a larger gap in your spectrum around 0. If you're looking for the intuition, suppose you just had one example. So you're at alpha approximately 0, right? You just have one example. Well, quite clearly, your covariance matrix would have one strong direction, and all the rest would be 0, right? So then your minimum eigenvalue would just be related to the norm of your one input. So that's why this sort of peaks up here. Okay. Another thing that these solutions reveal, which I think is critical, I really think it's a point that needs to be reiterated a lot when it comes to deep networks, is they care how they're initialized. So there is a strong impact of initial weight size on generalization dynamics, even in this simple case. So if you define the initialization noise ratio as the ratio of the size of your initial weights to the teacher's weight variance, then you can see it appears here. It appears in this expression, right? So in fact, larger initializations are going to perform worse. And again, the intuition, and I think it's straightforward, it's just you have this frozen subspace where you're not doing any learning. So anything you initialize in those directions will stay there. You're stuck with it. So to generalize well, you have to start with small weights if you're in this overdetermined regime. It doesn't really matter in the regime where you have lots of data because you're going to fully constrain your model. Okay, Another strategy that you can look at is early stopping. So we've seen that you don't always need to early stop, right? If you're sort of off in these wings, you may not need to early stop, but you can always early stop. And here I'm comparing in the blue curve the performance of the early stopping solution to the late stopping solution. So the late stopping solution, you see the spike around alpha equals 1, but if you early stop correctly, it's never really an issue. So overfitting is not a huge burden, provided that you're you're early stopping at the appropriate point. And in fact, in this case, you can compare the early stopping performance to the best possible performance. In this case, the Bayes optimal regularization is just L2 regularization of a particular strength. And you can see that, in fact, early stopping nearly saturates this. It gets almost the exact same performance. This is, of course, dependent on the exact problem formulation that we're looking at, so it won't always be the case. But at least in this setting, early stopping is extremely effective. And another aspect of these solutions that I think is quite interesting is how the optimal stopping time depends on the amount of label noise you inject. So remember that we're adding noise to the labels. This really is like, it's like you just mislabel a fraction of the MNIST examples, right? That's what we're talking about when we say the signal to noise ratio. And so the question is, how does the optimal stopping time depend on this label noise? And essentially the result is the more accurate your labels, the longer you're justified in training. And I think that it's very straightforward. You just don't need as much regularization to combat that randomness in your function. And it grows logarithmically in this case. Okay, so that was all for a shallow network, but how does depth change this story? So again, we can start by just switching back to the deep linear networks. So we have a teacher network here. It can still be shallow because, again, wouldn't gain anything from depth, but our student network will now be deep. And in this case, if you were going to do the full batch gradient descent, you'd have to run these full equations. You'd require n squared d parameters, where n is the number of hidden units per layer and d is the depth of the network. But in this instance, you can find a reduction. So here's a reduction, it's approximate, to n plus 1 parameters. And you notice that actually that's a substantial reduction, right? So we lost the factor of the square, and depth no longer figures into it. And if you look at these equations, essentially what it has the scalar u and a vector z. And u encapsulates the entire effective depth into this global scalar. And by the way, I think if you look at, so if you're here for Sanjeev's talk in the morning, he mentioned that you can get acceleration from depth. This is exactly that term, right? You're accumulating, your learning speed is accumulating into this scalar, essentially. Okay, so if we run this reduction, you can see that it's quite accurate for these different depths. And essentially, the punchline is that things look quite similar to the shallow case. The only real difference is you get this slight plateau at the beginning that you used to see in the training dynamics as well. And that comes from starting with small weights and being near that initial saddle point. Okay, so far everything I've talked about has just been linear networks. Of course, nonlinearity is essential if you're going to do a useful operation in the real world. So how does generalization performance unfold in sort of simple nonlinear settings? And in particular, the crucial question is, do any of these findings from the linear analysis actually hold when we take them to the nonlinear setting? So to look at this, we're going to look at a nonlinear student-teacher setting. So now I have a teacher network where I draw its parameters randomly, but now it's got a hidden layer with ReLU activities. And I'm going to have my student as usual here. And once I add nonlinearity, this new question presents itself, which is how many hidden units should I use, right? I can make this network very small, I can make this network very big. We'd like to understand the optimal size. Okay, so in these networks, I'm just going to show you simulation results. The teacher has 30 hidden units. The data set has 300 examples. These are quite small, right? But then the question is, how many hidden units should the student have? 5, 30,000. And here are some example results. So on the y-axis here, we have the error. On the x-axis, we have the number of hidden units. And this is trained just pure batch gradient descent, nothing, no bells and whistles. And what you can see is that if we run training for a very, very long time, we recover a spike right where the number of hidden units equals the number of examples that we presented. So that seems consistent with the linear case. But if we do early training, stop at the right point, then things just get monotonically better, essentially. And in this case, the largest model we tried was also the best performing model. And so this replicates at least one of these features of linear models, which is the worst case for overtraining, sort of at this intermediate model complexity. And also just to note that as far as optimal model size goes, in this case at least, you'd want to choose the largest one we did, right? Which happened to be 54 times larger than the number of examples. And we can't analyze this analytically yet, but we can just look at the spectrum of these covariance matrices in the hidden layer of these networks, which can give us some of the same insights that we've been looking at in the linear case, and just look at the empirical eigenvalue spectrum. And we see very similar behavior. So in this case where you have fewer hidden units than number of samples, again, you got a little gap around the origin. And if you're in the underdetermined regime, now you have your delta function spike at 0, but then a little gap at the origin. And it's at this intermediate case where you have lots of extremely small eigenvalues. And this is the point where the overtraining is the worst. And actually, it's quite fine for either of these ones. This is a very big model, right? Much bigger than your data set size. OK. So, I should have mentioned, this was for just training the readout weights of that nonlinear network. So the input weights were random and fixed. And there we saw that we qualitatively recapitulate this linear case. And in fact, as long as you're early stopping, bigger was always better in terms of generalization performance. We can also do a fully trained version, exact same thing, but now we're training both layers of weights. And again, we see a qualitatively similar pattern. So we have a spike in overtraining. At this time, it occurs at the number of free parameters in the model. And if you were overstopping, your best model size would be the largest one that we tried, which is substantially larger than the amount of training data. And finally, we can look at real-world data sets, right? So the student-teacher formulation is a strong assumption about how the data is generated. So we want to see if those assumptions are mirroring what we see in the real world. And so we ran some experiments on MNIST. And again, we see a peak in overtraining where the number of examples equals the number of free parameters. So I think that this captures at least some of the important issues that are going on in generalization dynamics for these networks. And the key thing is that it's the specific dynamics of gradient descent that are providing this regularization. It's the confluence of being in the high dimensional regime and the statistical properties of that give you this frozen subspace and that give you this protective Eigengap, which prevents overtraining. And a key part of this is you have to start with small weights. So if you start with large weights, you can have much worse performance from these large models. All right, so now we can also just ask if these linear results might explain some of the puzzles that people have been interested in as far as generalization dynamics go. And I just want to point out that these linear shallow networks, they're very simple models, show the complete pattern of findings that were reported in those papers. So in particular, if your network is underdetermined, then any data set can be fit perfectly, right? You just have so few training samples that it's no problem to fit your data exactly. But we've seen that generalization can still be good, provided that you're in this low SNR regime. So essentially, the idea is that the key here is you started from small weights, and that implicitly is controlling the complexity of the solution. And I think there's a very analogous to the case with SVMs. They work fine with infinite VC dimension kernels precisely because the capacity is controlled by the margin or the norm of the solution. Okay, so to summarize these generalization dynamics, in the high dimensional regime, overtraining is worse when the dataset size is exactly matched to number of parameters in the model. And I think, one comment here also is the analysis that I've been presenting is based on an average case analysis. It's not a worst case bound, right? And that means that we were able to get sort of an exact analysis of the simple case, but it is different from the approaches you've seen earlier that are trying to just bound the worst case performance. And we've seen that, at least in this case, it's extremely important to start with small norm weights. And I think that if you're thinking about the regime that we run our deep networks in, it appears to be this underdetermined accurate label regime. And in that regime, overtraining is not a problem. And again, let's just go through that again. So the reason why is when you're underdetermined, you have a large gap between the smallest eigenvalue, smallest non-zero eigenvalue, and the origin, which is protecting you from overtraining. And then you've got a lot of directions where your eigenvalues are exactly 0. So you have a frozen subspace where no learning occurs in the shallow case. So those two things conspire to allow you to learn well. And then the accurate label regime, I think, is also crucial. If you had added noise, if you were in a low SNR regime, then you can overfit substantially. And it's really the fact that MNIST and ImageNet and all these data sets, they are accurately labeled, and they're deterministically labeled, essentially, right? The correct answer is a deterministic function, essentially, of their input that allows generalization to be quite good. And you can train them with full batch gradient descent with no regularization, and they will still work well. And in that regime, the largest neural network that you use will likely be the best one. So if you're interested in more on this, this is also available on arXiv. Okay, so in this talk, I focus mostly on minimal models. By design, I mean, I think it's important to try all approaches to understanding deep networks, but the one that I'm taking is trying to strip away things, see how simple you can make these networks and still get at the core phenomena that we're interested in. And nonlinearity is essential for a deep network to work well in practice, but it may not be necessary for understanding certain aspects of its dynamics or its generalization performance. And I kind of view this like analogous to, you would learn about linear control theory if you're an electrical engineer, but no one thinks a space shuttle is a linear system. But it's still very important to get those foundational concepts right. And same with linear circuit theory. No circuit that's ever been built is linear, but it's an important window into these dynamics. So just to conclude, learning in a deep chain-like structure can be difficult and slow depending on how you've initialized these networks. We can sort of understand aspects of this using these deep linear neural networks. And a key difference that arises in them is their sensitivity to initialization. I think this is extremely important also to the brain sciences. What's in the network determines how quickly it will learn new information. And I think there's much more to be learned. So with that, I just thank my advisors, in particular Chaim Samplinsky, and Surya Ganguly and Jay McClelland, with whom I did the training error work. And thank you very much.
Thank you, Andrew. Questions?
So I'm wondering, in the generalization part, when you compared linear networks, deep to shallow. Yeah, so in that case, if there are at least as many examples as there are dimensions, then there is a unique model that has the lowest training error. And if the linear network eventually reaches that, these things are going to generalize in exactly the same way. And so I was wondering if you see any distinction between deep and shallow in terms of generalization when the problem is overdetermined and when it's underdetermined. I know there are some works like saying that deep networks are biased towards lower trace norm or things like that, but I was wondering what your perspective is on, specifically on the role of depth in linear networks for generalization.
Yeah, that's a fantastic question. We're still working on chasing down all the details there. So I thought they would be identical too. Turns out they are slightly different. If you have a lot of data, they're the same. And there's no two ways about it, they're the same. Once you go to alpha less than 1, which is I think where sort of the realistic regime for deep networks are, then they actually do behave differently. So I didn't mention it, but in the shallow network, the frozen subspace is genuinely frozen. You make no movements in it whatsoever. In the deep network, it's actually not true. You can move in the frozen subspace. And to see that, so essentially, if you started with large random weights at a low layer, suppose it was just a 2-layer network, and you have large random weights in the lowest layer, then the changes in your higher layer are going to be in the directions of those random weights, which is not the directions of your data. And that's a problem, because when generalization examples come in, they might be in that frozen subspace, and you'll do worse. So they actually can give different results, but I haven't fully explored that space. I mean, the frustrating part is a reduction is nice, but it's much better to have exact solutions. But I haven't been able to get there yet.
Other question?
I have a neuroscience-related question. So you've shown that these large initial weights are good for learning because you escape the plateau in the beginning. On the other hand, they're bad for generalization. Do you think that that's a necessary ingredient for episodic memory in general? And if so, do you think that like episodic systems like the hippocampus distinguish themselves from other systems based on this ingredient for large initial weights?
Yeah, I think that could be exactly right. So let me see if I have a backup slide on. There's another. Well, this will sort of demonstrate the point at least. Here I'm training a depth 100-layer nonlinear network. And all I've done is tried different initialization schemes. So the green line is sort of, at the time, it was the best practice initialization scheme for these 10H networks. The purple line is using orthogonal initial conditions, which I talked about briefly. And the blue and the red lines are just using even larger initializations. You just multiply the initial weights by 1.2, or on this case, it's 5. And you can see that these networks train much faster. And we're talking vastly faster training speeds in these very deep networks from using these large initial weights. But there's a problem, which you pointed out to, which is that from a generalization perspective, large weights are hurting you, right? So this is training error. And there is this trade-off, and watch archive because we're close to getting this out, but basically you can formalize this. So there is a trade-off between your generalization accuracy and your training speed, at least in these deep linear models. So that's sort of the high-level picture. I think that's true. And then specifically regarding hippocampus, yeah, I mean, I think you could model hippocampal learning as sort of you have one strong initial weight matrix that's sort of orthogonalizing everything, and then you're just learning a final recurrent matrix, and that would be much faster. So that's getting at another assumption I made, which is this balanced assumption. So if the layer strengths aren't all equal, if I took the first layer of my network, multiply by 1,000, take the second layer, divide by 1,000, that has very different learning dynamics. It turns out it learns much faster. So I think that might be a reasonable model of the hippocampus.
Any other questions? Okay, I think people need coffee by now, so we will break and then come back at 10 to 4 for the last two talks of the day. Thank you, Andrew.